Hello everyone, welcome to this video taking a look at the velocity problem, which is the second of our motivating problems for studying limits, which are going to be the first topic in the course. So the velocity problem asks the question, how can we calculate the velocity of some object at a given moment in time, if we know its position, for instance? So before we tackle that, let's look at some easier cases. So for instance, if an object has constant velocity, then, okay, as we learned in school, a long time ago, if an object has constant velocity, then the velocity is the change in position divided by the time elapsed. Okay, speed equals distance divided by time, essentially. But what about if the velocity is changing, right? Which is very, very common in life, right? If you're driving a car, hopefully your velocity changes. Maybe you slow down for a stop sign, or at least I hope so. And then, okay, you get to go fast somewhere else if there's not too much traffic. So if we do the same calculation, but the velocity is varying, so if we do the change in position divided by time elapsed, then instead we get the average velocity. Okay, so in general, if the velocity is varying, distance divided by time or change in position divided by time, that will give us the average velocity over the time interval. So for example, if I'm feeling healthy, if I'm doing well one day and I commute by campus to bike, then by bike, then the distance is around 1.6 miles. And it takes me about 8 minutes on a good day, which I converted to hours, which is 0.1333 and so on hours. And my velocity varies quite a lot, right? If I get on my bike or if I'm at a stop sign or something and I'm following the rules, then my speed will be 0. But if I'm going through the park or I'm going fast along the road, then my velocity will be very quick. So my velocity varies. But if I do the calculation, then my average velocity is my distance divided by my time. It's around 12 miles per hour. Okay, so that's the average velocity. Okay, but what about if we wanted to find the instantaneous velocity at some given moment in time, right? I mean, if you drive somewhere, if you take a trip and you don't want to get a speeding ticket, it's not very good to say, my average velocity was under 65 miles per hour. If at some point you were traveling at 100 miles per hour, that would be very bad, and you definitely shouldn't do that. So we have to be interested also in instantaneous velocity. So how do we do that? The answer is to find the limit of average velocities over shorter and shorter time intervals. Okay, so why would this make sense? If I think about driving a car, say I'm driving somewhere, so say I travel for, I don't know, for an hour, I start in the city and then I get on the freeway and then I get off and I'm in the city somewhere else. If I do the calculation distance divided by time for the whole thing, it's not going to tell me very much about my actual speed at any given moment in time, right? It's just going to tell me over that whole 1 hour trip, it's going to tell me what my average speed was. But if I break it up into shorter and shorter chunks, then it's going to give me more and more information, right? If I look at the first couple of minutes, say I'm driving in the city, and I do distance divided by time, that's going to give me a pretty good approximation of what my velocity was in the city. Or if I look at, say, minute 30 to minute 35, say, and I do a calculation, it's going to give me a good idea of what happens on the freeway. And in general, the smaller the chunks you break it up into and do this calculation over, the more accurate information you're going to get about any given moment in time. For instance, if I do the calculation distance over time for 30 minutes to 30 minutes and 30 seconds, that's going to give me a very good idea of what my speed was at time 30 minutes. Okay, so in general, the smaller the chunks you break it up into, the better the average velocity, or the closer the average velocity is going to be to your true velocity at a given moment in time. So if we really want to find the true instantaneous velocity, we should look at the pattern of average velocities over shorter and shorter intervals. Okay, so if we want to find the instantaneous velocity at time t, we look at shorter and shorter intervals that start or end at t, and we find the average velocity over those intervals by using the previous calculation, distance over time, and then we see what the pattern looks like. And okay, here are two things to keep in mind, which were very similar to the previous topic with the tangent problem, just in a slightly different context. One is, as we talked about, average velocities over shorter time intervals give a better approximation of instantaneous velocity, right? If you calculate something between 30 minutes and 30 minutes and 30 seconds, that's going to give me a very good idea of what my speed was at time 30 minutes. If I do the same approximation, if I do the same calculation for 30 minutes to 40 minutes, well, it's not going to be quite as good an approximation of my speed at 30 minutes. Okay, and it feels like we are looking at shorter and shorter intervals as with start or end at t, we're looking at shorter and shorter intervals. It feels like, we want to just, knock it out and make the interval as small as we like, just make the interval have length 0. But of course, that doesn't make any sense, right? We can't do a calculation over an interval that has length 0. It wouldn't be an interval, it would just be 1 point. So we can't make the endpoints of the interval equal, so we really do have to do these calculations and look at what happens, what is the pattern, as they get smaller and smaller, right? We can't just plug in. Okay, so let's look at an example. So suppose the height of a rock thrown upwards is 10t minus 1.86 t squared meters, where t is measured in seconds. Okay, so who knows if this actually corresponds to the real world, but just an example, here is the height of a rock where t is measured in seconds. And our problem is to find the instantaneous velocity at time t equals 1. Okay, so if we go back to the algorithm we just talked about, if we want to find the instantaneous velocity at time t, we said we should find the average velocity over shorter and shorter intervals which start or end at t, in this case, starting or ending at 1. Okay, so that's what we just said. So for instance, for the time interval from 1 to 1.01, let's compute the average velocity. Okay, in that case, the average velocity is supposed to be distance traveled divided by time elapsed. So if we look at the distance over the interval from 1 to 1.01, the distance is just the change in height of the rock, right? So we have to calculate the height at time 1.01 minus the height at time 1, divided by the time, which is 1.01 minus 1, and okay, plug in and see what we get using the equation y equals 10t minus 1.86 t squared. I'll spare you the calculation, and we get around 6.2614 meters per second for that time interval. Okay, and we said we are supposed to do this over shorter and shorter intervals. So here's the same calculation, just done over different intervals from 1 to 2, 1.01, and so on as they get smaller and smaller. Okay, and you might say, why did I pick these numbers? Why did I pick these intervals? Well, I just picked these intervals just to try to see the pattern. So you could have also picked 1 to 1.05, 1 to 1.005, and you would have got very similar outcomes. So we just picked some intervals. But what should be true is that as the intervals get smaller and smaller, the average velocities start to settle down on some number. And this will be called the limit, right? And this is supposed to be the instantaneous velocity. And if we look in this case, the limit, or if we look at what happens to the average velocities, they're getting pretty close to 6.28, at least to 2 decimal places. So in this case, we can say the instantaneous velocity, which is supposed to be what happens to the average velocities as we take shorter and shorter time intervals. In this case, the instantaneous velocity at time t equals 1 is approximately 6.28 meters per second. Okay, so that's our example. Okay, so just the takeaway from this video is, in general, if the velocity is changing, then distance divided by time will give you average velocity. If you want to find instantaneous velocity at a given moment in time, you should look at shorter and shorter intervals starting or ending at that moment, calculate the average velocities, see if they settle down into a pattern. Okay, here there are limits in hiding yet again. Okay, thanks everyone. See you next time. Bye-bye.